show up as we move forward. Okay, great. So thanks everybody for joining us today for this week's GIS Planet Seminar. Today, Alessandro Regorda is going to tell us about rifting Venus and insights from numerical modeling. So can you try to share your screen, Alessandro? Let's see if it works.
Okay.
And Chris, I'm going to make you a co-host in case something happens to me.
Does it work?
It's looking good.
Okay, cool. Okay, can I start? Yeah.
Yeah, please.
Okay, cool. So thanks again for inviting us to present the result of our work. I'll say something about rifting processes on Venus. We studied them by means of numerical modeling. So even if we do not currently observe some kind of plate tectonics on Venus, there are some evidences that Venus might have experienced in the past some kind of tectonics. In fact, there are some structures that have been correlated to some kind of tectonics, like the corona, but there are also widespread observation of rifts on Venus. They are called chasma or chasmata, and they have been interpreted as normal fault-bounded gravity structures. These structures are typically wider than what we can observe on Earth, and this could be related to a stronger rheology of the crust. So despite being a prominent feature on its surface, little is known about the process responsible for creating rifts on Venus, beyond the assumption, of course, that they are extensional features. So since rifting on Earth have been extensively studied through modeling, we decide to adapt and use a numerical code Falcon to assess how rifting processes works and which numerical ingredients are needed to successfully model rifting on Venus. In particular, we take into account pressure, temperature, and gravity of Venus on the surface. Of course, they are very different of what we have on Earth. Since there are different hypotheses on the average crustal thickness for Venus, we decide to test two thicknesses for the crust. And since we don't have any direct information on the rheology and composition of the crust and the mantle of Venus, we tested different crustal and mantle rheologies. And also this one is more a numerical issue than Venus related. So just to briefly introduce this problem, in modeling rifting on Earth, initially weak zones are used to simulate heterogeneities in the lithosphere by introducing some areas characterized by lower viscosities. So these help the localization of the strain rate, the accumulation of the strain, and the development of structures typical of rifting. So since we don't know how rifting can work on Venus, we decide to test different initial weak zones just to be sure that what we choose will not influence the evolution of this rifting. Of course, there are many parameters we didn't take into account, like different thermal gradients for the crust and lithosphere. We just tested one. And we also tested just one thickness for the lithosphere and one velocities of the extension. And it's just a 2D, not a 3D model. And there are many other things we didn't take into account, but okay, this is the model setup we used for all the models. The left side is the model setup we used for Earth with the 120 kilometers lithosphere, while for Venus we used a 55 kilometers lithosphere. On the contrary, the crust, the thickness of the crust is the same for both Earth and Venus. And there are different thermal gradients. The black line is for the Earth and here for Venus, and different profiles. This is the typical profile of the Earth. For Venus, we obtained something different, but I will say something about this later. And this is one of the weak seed, or the weak zones we use to favor the development of rifting. This is placed here in the mantle. We tested another one in the crust. and we also test another kind of weak zones characterized by randomic weakening of all the lithosphere. So it's this last weak zone is more realistic. So in this presentation, I will show you at first the effect of stronger rheology for the crust and the mantle in the case of Earth conditions. After that, I will show you some results introducing the pressure, temperatures, and gravity of Venus using the rheology, the crust rheology of the Earth, so weak rheology. And then I'll show you when I show the result of the models characterized by all the Venus conditions, so pressure, temperature, gravity, lithospheric thickness, and we tested the effects of different weak seed and crustal thicknesses. And in the end, I will show you some comparison between our results and observed topography and heat fluxes. These are the parameters we used. In particular, just for the rheology, we used the wet quartzite and a wet anorthite for the upper and lower crust in case of the Earth, while we decide to use a dry metal and diabase for both upper and lower crust in a case, for Venus. And for the mantle, we tried both dry dunite and dry olivine rheology. Very briefly on the parameter for the plasticity, we didn't change these parameters between Earth and Venus, and that's because they are not well constrained, not even for the Earth, so certainly not for Venus. And we are aware that they can have some effect on the evolution, and so they surely worth a deeper analysis. So this is the first model I'll show you is just a test model, a final benchmark, because the numerical code we used was new. So it was fully benchmarked in every features, but we decided just to make a last test just to verify that the code could simulate correctly this kind of tectonic setting. So this is in case of the Earth conditions, there is no melting, just a very simple rifting for the Earth. So we can see initial conjugate faults, and it evolves in a symmetric rifting with upwelling of the crust, and well, there is no melting because we didn't implement it. But all is very symmetric, and this is very similar to what has been observed previously by other authors. So we can say that our code simulates correctly this kind of problem. This is the reference model we used. So for the Earth, pressure, temperatures, and gravity for the Earth. The seed is in the mantle, weak rheology, and a thick lithosphere. As seen before, there is the development of these conjugate faults, symmetric conjugate faults, but in time, this rifting evolves in an asymmetric rifting. And however, there is the upwelling of the mantle here, and there is the development also of PT conditions compatible with melting. Melting here is just this brown area, and so it is what we can expect from a rifting for the Earth. And of course, there is the development of some topography. Is asymmetric with two heights and the sides of the rifting and a basin. So what if we change the rheology of the crust? So same model as before, but with a strong crust. Sorry, nothing really changes. There is of course an increase of the viscosity in the crust, but the general evolution is very similar. It's asymmetric, but the trend of the folds around which the strain accumulates is very similar of a typical model of Earth. However, the evolution is a little bit slower. This is because of the stronger rheology, and in fact, the mantle upwelling is a little bit less evident. There is no crustal breakup after 10 million years, and the mantle melting is less extended. Differently, the topography is different, and in this case, the black line is the topography for this model in comparison with the previous model with the dashed red line. You can see that there are both higher maximum and lower minimum. So the crustal rheology has an impact on the topography. Same model, but with a stronger mantle rheology. Again, nothing happened, nothing interesting here. Higher viscosity also in the mantle, in the asthenosphere, and it's even slower than the previous model with less upwelling of the mantle and no welting. However, it's just a matter of time, in maybe 2 or 3 millions of years of additional extension, there will be a melting also in this case. And the changing of the mantle rheology does not affect the topography. This is one black, this model, in comparison with this dotted red line for the previous model. And you can see that the topography is almost the same. So no changes in topography, we change the rheology of the mantle. In these models, there is the crust is characterized by a weak rheology, so wet quartzite and wet anorthite, and we introduced one at a time pressure, temperatures, and gravity, and both of them, pressure and gravity. This on the top left is the reference model, and we can see that introducing pressure, gravity, or both of them doesn't change. There is this still asymmetric rifting, same pattern of these folds characterized by high strain accumulation. And the only thing is the extension of the melting. If we consider surface pressure of Venus, the pressure also in depth is higher, so the melting is less extended. On the contrary, for the gravity of Venus, which is lower, the pressure also in depth is lower than on Earth. So in this case, the area characterized by partial mantle melting is more extended. It can't be seen here, but it's here. In case of pressure and gravity, these are the lines of the pressure for the Earth in blue and Venus in red. And we can see that for the higher pressure on the surface, on Venus, there are higher pressure just above 3 kilometers depth, while below, the gravity has a main role. So below 3 kilometers, the pressure on Venus is lower than on the Earth. And in this case, in fact, the extension of the melting is more extended than for Earth. So on completely different case, if we change the temperatures at the surface, so consider the temperature on surface for Venus, nothing happens. This is in case of a thin lithosphere, so 55 kilometers lithosphere, and we can see that there is no accumulation of strain. The lithosphere thins homogeneously, but there's no evidence of any structures like we can observe for rifting. And this last test was with temperatures of Venus at surface, but with a thicker lithosphere, like on the Earth. And in this case, there are some accumulation of strain in between the upper and the lower crust, but none of these structures reach the surface. So also in this case, there is no development of topography and no rifting-like structures on surface. Just to summarize this first part, then I move to the more realistic Venus models. We saw that there are some initial symmetric strain localization but the rifting evolved in asymmetric riftings, irrespective of the crustal and mantle rheology chosen. For all models, there is, for the Earth conditions, for the models, there is mantle upwelling and PT conditions compatible with melting, but of course, the evolution is slower in case of a stronger rheology. The topography is affected only in the case that we change the crustal rheology, while the mantle rheology does not impact the topography. And we saw that pressure, gravity, and does not affect the evolution of the rifting, while high surface temperatures of Venus does not allow efficient strain localization. And so it prevents the development of a continental rift. So from now on, all the models will be with the conditions of Venus in terms of pressure, temperatures, and gravity. These are the models with a weak crust, so wet quartzite and wet anorthite crust. 4 different seed. This first column for the crustal seed, this for random seed, and this with the mantle seed, and with 2 different crustal thicknesses, 35 kilometers and 25 kilometers in the last column. All of these models have a lithosphere of 55 kilometers. So there are no differences if we consider the models with 35 kilometers crust. There is no strain localization, there is no accumulation of strain, there is only minimum accumulation of strain here, but it's very low, between 0.1, and there are no structures that can be related to some kind of rifting. And the same from the random seed. This accumulation of strain you see here is the imposed accumulation strain at the beginning of the model to simulate the weakening to favor the localization of the strain. So there is no additional accumulation of the strain. So these models are very similar. There is no impact of the weak seed on the evolution. While if we consider a thinner crust, something seems to happen. There is a sort of a development of these conjugate folds. However, the strain rates are much lower than what we observe for Earth, about 1 or 2 orders of magnitude. And so the accumulation of strain is low, and there are no, again, evidences of topography and rift structures. So probably a stronger rheology is mandatory to have something. These models here are with a crust of 35 kilometers in case of conditions on Venus, thin lithosphere on Venus, and different seeds: mantle seed, crustal seed, and random seed. We can see that changing using different seeds, the evolution changed a bit. It's faster for the crustal seed and the random seed, and in fact they develop these folds characterized by high strain rates, while they are lower in case of mantle seed. And in fact, in case of mantle seed here, there is no accumulation of the strain, while finally we have some strain accumulation for these 2 models. However, there is no mantle upwelling and no melting. And this is because we can see here that there is accumulation of strain, but there are no high strain rates at the end of the evolution. This is the end of the evolution. And so this accumulation of strain is due to the initial strain in this area. But during the evolution of the rifting, these strain rates migrate towards the border. And so there is the development of new area characterized by in which the strain accumulates here and here. Same for the random seed, a little bit different, but the same idea. And so the deformation is distributed along the whole lithosphere here. And there is no just one zone in which there is mantle upwelling, and so the development of PT conditions compatible with melting. The topography are, for these two cases, are almost not topography in case of the mantle seed, but for these cases, the topography is a little bit different from what we observe for the Earth. The black line is the topography, and we can see that there is some basin, but in the middle of the basin, there is a peak of topography. Also for the random seed. This peak is in correspondence of the higher accumulation of strain. And in correspondence of this peak of topography, there is a decrease of the heat fluxes. The heat fluxes are in the red lines, and the decrease of the heat fluxes in this portion is about 10 to 20 milliwatt per meter square. So considering the same model, so 35 kilometers crust, but with a crustal, stronger mantle rheology, nothing is very similar to what we saw with the previous models. Again, mantle seed, crustal seed, and random seed. The evolution is faster in the case for the mantle seed with respect to this crustal seed, but there is the same behavior. So an initial area characterized by high strain rates, but after that they migrate toward the border. And for all models. So also in these cases, this distribution of the strain does not allow mantle upwelling and mantle melting. And as seen for the previous models, there are these peaks of topography inside the basin in correspondence of the high accumulation of strain. And as before, the heat fluxes in red decrease in correspondence of these peaks of about 20 milliwatt per meter square. Things are different if we consider 25 kilometers crust models. This is with a dry olivine mantle. And again, mantle seed, crustal seed, and random seed. And the velocity of evolution are a little bit different. Seems to be faster for the crustal and random seed, but in this case, also model with the mantle seed is able to accumulate strain and to develop a topography. The difference between the model with the thicker crust is that in these cases we didn't observe any migration of the strain rates. So in this case there is the possibility to have mantle upwelling and so to produce PT conditions compatible with mantle melting here and here. And another difference is on the topography, in particular for these two models. We can see that there are wider and deeper basins with respect to models with a thicker crust. And there is no a high peak in the middle of the basin, some sort here, but however, it's different from what we observed before. And in correspondence of these basins, there is an increase of the heat fluxes, this is the red line, of about 70 to 80 milliwatt per meter square. So the behavior of the heat fluxes is very different. And the same thing we can see the same thing if we change the rheology of the mantle. In this case, all the models are fast to evolve. And for all models, there is a lot of accumulation of strain in the central part of the domain. So it allows mantle upwelling and mantle melting for all models. So without no migration as the previous models. And as previous models, the topography shows also a deeper basin, and there are no peaks in the central part of the basin, and also the heat fluxes in red are higher inside the basin of the rifting. In this case, up to 200 milliwatt per meter square. So just to summarize all these things we observed, well, no models with a weak rheology, so quartzite and anorthite for the crust. None of these models show any strain localization, mantle upwelling, etc. For any seed and for any crustal thicknesses. So a stronger rheology for the crust is mandatory to have strain localization. The only one is this one, but yeah, generally with a stronger rheology of the crust, there is strain localization, and irrespective of the seed chosen. Differently, mantle upwelling and melting occur only if we have a thin 25 kilometers crust. So models here and here. There are some differences also in this case for different seeds, but that we can see two trends: melting and mantle upwelling for a thin crust, no melting for a thicker crust. These are the stress profiles of our models in case for models with diabase and dunite rheologies. And we compared our profiles with the one from Bern 2021. We can see that in this area, the creep portion is very similar. These differences are due to differences in the thickness of the crust, but the trend is the same. And there are some differences here in the plastic layer. However, first of all, we can see that a stronger rheology is needed to have this plastic layer. While if we consider a quartzite rheology for the crust, all the behavior is a creep, so no plastic layer. Our layer is similar in thickness to what observed or inferred by Bern. There are differences in the maximum yield stress, but this one is related to the parameters of the plasticity we chosen. And if we choose those parameters, these lines will change. But I think that will not affect deeply the evolution of the rifting. The main thing is to have a plastic layer. And our maximum yield is about 80 megapascal, and this is in agreement with values calculated for tectonic processes associated to or a plutonic squishy lead or a plutonic episodic lead regime. So we are in this area here, and this is the same for this maximum yield stress. We are here. Just to finish, these are the average of the heat fluxes. Is averaged on all the weak seeds. So in blue, light blue, the models with the 35 kilometers crust, and yellow and orange 25 kilometers crust models. And they have two different trends. It's clear the 35 kilometers crust models show this decrease in the heat fluxes, while the models with a thinner crust show a clear increase of the heat fluxes in correspondence of the rifting. And one other thing is that in the far field, the heat fluxes we found are in agreement with the estimated global average for Venus. And we saw that the thicker the crust, the higher is heat flux. So maybe a crust thicker than 35-40 kilometers will be too much to have this kind of heat flux. And finally, the topography. We average the topography for different seeds and compare them with the topography from the Ganis chasm and Devana chasm. There are two different trends. For the 35 kilometers crust, we can see this peak in the middle of the basin, and which is in agreement with this peak observed in the Ganis chasm. While on the contrary, the Devana chasm has these deeper and wider basins, which is in agreement with our models with the 25 kilometers crust. So to conclude, we saw that the choice of the initial weak seed does not affect the evolution of the rifting, while different crustal thicknesses produce a distinct topography and heat fluxes. So they have the crustal thicknesses have an important effect. A stronger crustal diabase rheology is required to localize strain and to develop rift in case of Venus conditions, of course, while a stronger mantle rheology does not clearly impact the evolution of the rifting. we observed that only a thin crust produces the melt required to support the hypothesis of Venus being currently volcanically active. Therefore, our model suggests that a thin crust with a global average of 25 kilometers could be the most likely crustal thickness on Venus. And the surface topography produced by our model fits well with the topography both of the Ganis and Devana Chasmata for different crustal thicknesses. So we can speculate that differences in these rift features could be due to differences in local crustal thicknesses. Thank you.
Okay, great. Thank you, Alessandro. That was really great. Learned quite a lot there.
I know.
Are there any questions for Alessandro from any of the audience? You can just unmute yourself if you want to chat. Maybe I can ask a quick question. I noticed when I was reading through the paper in your table 3, I mean, you varied a lot of parameters, obviously, so you can't run everything, but I noticed that your viscous weakening, you fixed them all to 10, except for the very first one for Earth, I guess. So could you talk a bit how that might affect your results? Would that affect anything? Probably nothing to do with the crustal thickness per se, but maybe more to do with, is this related to mantle upwelling speeds and things like that?
Okay, well, we saw that introducing the viscous weakening for Earth conditions, this creates this asymmetric rifting. And this could be related to the fact that viscous weakening mainly affects the viscosity in the just below the lithosphere. Yeah, it could have some effect on the velocity of evolution, also in case of Venus. But the parameters chosen are also in this case also all the parameters. So friction angle, cohesion, and all these parameters for the weakening are not well constrained on any planet. So yeah. Of course, they could change something. We don't know exactly how. And there are some papers that study this, but for these differences in symmetry and velocity, that does not really impact the general evolution of the rifting. But yeah, I think that these plastic parameters should be studied more in detail, all of them, just to verify if they really have some kind of impact or not.
And do any of these plastic parameters also relate at all to the water content in any aspects?
Usually, no. I mean, there are no differences between parameters that are used for also on the Earth for continental crust, oceanic crust, and some people use, for example, 15 degrees for the friction angle, others 25. So yeah, it could be related to water. We tried to consider the water for what concern the creep part of the viscosity. So the diabase rheology. The idea to choose this strong diabase rheology is that Venus is thought to be dry, and so yeah, I think just my opinion, but I think that in general these parameters has maybe a greater effect than the plasticity parameters, but not sure.
Okay, yeah, and I also noticed that when in your models you were using these dry upper and lower crust Have you thought about maybe changing that? Because we don't really know the water content at all. And if you used a wet lower crust, do you think that that would make any difference? Because maybe the drying happens in the upper crust rather than the lower crust, for example.
It could. Yeah, that thing could be change something. Could be change the possibility to accumulation of the strain. Because if we consider a wet rheology, of course we should use a weaker rheology, and using a weaker rheology for the maybe not. Now I'm thinking about that, because if you if you see this, the stress profile, the plastic layer is just in the first 8-9 kilometers, and below that is just a creep behavior. So if we change this, I'm not sure, it could be weaker here, but maybe it won't change much. Oh no, well, no, this is the lower crust is here. Yeah, but it's very low. So yeah.
So it's already
maybe
very low.
Change something. Yeah.
Won't change much. Okay.
Yeah.
I see. Let me ask you more questions. Unless someone else asks more questions, I'm going to ask another question. So, toward the beginning of your talk,
I can ask a question, Mike.
Go ahead, Joao. Please, yeah, go ahead.
You can go.
Go ahead, please.
No, it's just something that I kind of always bugs me a little bit. But I would like to have your feeling. I kind of ask this to everybody that works on Venus. Is what do you think are the timescales of the structure that you observe now on Venus? Do you think that they are relic? Do you think that they are frozen? Could they be? I know that uncertainties are a lot, and it may not. What's your feeling from having running these models?
Well, honestly, I have no idea. Maybe Iris can say something. No, honestly, I wouldn't say. I can't say anything about that. Yeah. So.
No, okay. It's an honest answer. Huh? It's like there could be something there. I don't know, but yeah, we need the missions. We really need the missions.
Well, yeah, that kind of ties into a question I was thinking about. And maybe Iris can comment on that too. I mean, we're going to have this really nice subsurface radar that comes with the Envision mission, which claims it will go hundreds of meters deep in some cases. Do you think that will help us put some constraints on exactly what Joao's asking about, in a sense? Like, because we're always wondering how old the surface is. We have crater dating and stuff, but for the basaltic flats, we have very poor constraints, for example. So I wonder, do you think that will tell us something about, what is the real rheology of the upper crust, and maybe a bit about, strain rates and things of that nature, or not?
Maybe they, maybe they can say something about the rheology, but it could be useful for to compare these models with what we know a little more about Venus. So maybe we can make some better comparison.
I also think some of the missions. I was just saying, I think some of the missions are trying to distinguish between basaltic and felsic stuff, so that might help as well. I'm not sure what these models. I mean, ground penetrating radar is very cool, but our models don't really work well in like the scale of the first 100 meters or so. So not entirely sure. Maybe you can do well. I don't know. I have been talking with Rich about potentially looking at like using Envision if they do something different. I'm not entirely clear how it works. If they do something different, they could potentially observe like strain and potentially earthquakes or something like that. And if you apply that to specific settings like rifting, that could give you an indication whether or not something could be active, because we can kind of try to extrapolate how much seismicity we would expect from rifts on Venus compared to what we know from rifts on Earth. And you know, that is one way these models could be useful or could be extended to kind of look at those things if we could get that information from Envision.
Yeah, if they can get some information about the strain rate on surface or something like that, it could be useful to use maybe a better extension of velocity, because we just use velocity. We don't know if it's realistic or not for Venus, and knowing better maybe the strain rates on the surface on these nearby the structures would be useful to better constrain the velocities.
Right, because you don't expect the strain rate to be uniform, obviously, right?
No, maybe at the beginning, but after the development of these structures, conjugate fold structures, it changes. Yeah, we see the strain rates are very high here, and above for that are low. So if we know that there are some areas with very high strain rates, and if we know also maybe the order of magnitude, more or less, we can try to verify if the velocity is correct, how the velocity, or how much could be the velocity, and these other things.
Yeah, I really liked how your models were able to fit those two chasmata. That was really amazing, and how it tied directly into crustal thickness. I thought that was really remarkable.
This one, the topography.
Yeah, this was amazing.
Yeah.
I thought.
Yeah,
That's really encouraging. Are there any other large chasmata you can compare your model to? I mean, these two work very nicely. Or are you hiding the other 5 from us?
no, I won't say anything about that. No, it's difficult to find some topography of the or
Resolution so low.
yeah. So we used what we found, and luckily they worked.
Yeah, I think this was really beautiful. Very nice stuff. Definitely. That's your calling card for your work, I would say. Do you have another question, Joao?
I have many, but I'm just kind of trying to. Now, one is more a comment. I think these works are really important because I think you'll get a lot of new data, but in a way, it's good to kind of anticipate what to look for, and even when the instruments are in place, to choose places and stuff. Because Iris, you were mentioning that they were trying to do something with the earthquakes. It's like radar thing that they will try to do different passes and do some kind of interferometry. That will be.
Yeah, I'm not entirely sure, but Richard Gale, he was the original PI of Envision, so he knows the mission inside out. And we were talking about it because we have this ISI team where we try to do a bit of Venus seismology. And then he was like, yeah, if they would only do that, something that I can't articulate myself, then we can actually, maybe look a little bit at earthquakes on Venus already with Envision in a very primitive way. But I think they have chosen not to do that for reasons that I'm not entirely clear on. So that is one of my to-dos for the next couple of months, to look into that and then write something about that. And then on the other future wish list that I have, which probably many people share with me, is that it would be, we would like to look into what are the best methods to detect seismicity on Venus, and could we propose some kind of concept of, an ideal seismological or geophysical mission, kind of, in the same way that InSight was really geophysical focused. Could we, propose something for Venus? Because it takes an enormous amount of time before these things actually, reach the end stage. So starting to think about it now might make sense.
And when you mention earthquakes, it's like really measuring the earthquake, or is measuring the surface displacement, for example, or that will be different thing, no? Like to kind of do
Yeah, different things. I mean,
movement of
probably
like the movement of the surface, because that
Yeah.
you could.
Probably initially the like with Envision, I guess that if there has been a change, that's very promising. But with the detection methods that we want to look into a bit more in the next year or so with the team, we are thinking of, seismic waves and stuff, potentially most likely in the atmosphere, because that's probably the easiest way to do it. But yeah.
Yeah, the atmosphere is
Okay.
much more tightly coupled to the surface than it is on Earth, given its thickness.
Exactly.
And its scale height's a bit lower. So the idea, I think, is exactly to look for these waves in the upper atmosphere. And I think yours is right. There has been this idea from the beginning from Richard Gale and company, to look for these kind of upper atmosphere waves. But yeah, I don't know the status then. Maybe we'll find out next week if there's any chance, or this week, sorry, if there's any chance they will get something like that. But I have the feeling that you're right, that they have decided not to go for that on this.
Exactly.
So we'll need to think of other ways to look for these kinds of things.
Yeah.
Okay.
Let me ask one other question. Early on, you were talking about, early in the first half of your talk, about the lithospheric thickness, and you were saying that it looked like thin lithosphere was ruled out by your model generally. I didn't quite understand why.
No, just we just think to use just a thin lithosphere, because there are previous models for the corona from Geria and Gulke that use just 55 kilometers lithosphere. So we decided to use that thickness, but yeah, we could try with different thicknesses. I know it's something we didn't test.
Okay. I guess Geria and company are using Stag YY to test some of these things. Is that
I3 Elvis? Stag YY is full type.
Yes.
Oh yeah, sorry. I thought they were buddies. I can't keep.
I mean, they are, but they're different codes. It's odd.
I see. Okay, cool. Thanks. Yeah, I loved all the names of the models in the paper you pointed out. They're really cool. You guys, you geodynamics, geophysics people have cool model names, I have to say. So. Awesome. Well, are there any other last questions for today? Okay. Feel bad Joao and I monopolized all your time, but that was really great, Alessandro. I think that was fantastic. I learned a lot. I think all of us did. And thank you for trying to bring it down to our level. It was really cool.
Well, thank you for giving us the opportunity to speak about that.
Absolutely. Okay, I'm going to try to say goodbye then. And thank you all for joining today. And see everybody in a few weeks. And see a couple of you tomorrow at the Envision meeting.
Yeah, have fun at the Envision meeting.
Yeah, we'll try. Definitely. Take care.
Bye-bye.
Bye.
Thank you.
Thank you.
Bye. Thank you, Mike.
Thank you.